Welcome to the deep dive. Today, we're skipping the usual scroll and diving straight into chemistry. Getting our hands dirty, you might say.
Metaphorically speaking, of course.
Right. We're looking at a whole series of experiments trying to really understand chemical reactions.
Exactly. Think of it as a lab tour, but, for your ears, we've got quite a variety lined up.
Yeah, things like calcium carbonate, copper sulfate crystals, those blue ones.
Mm-hmm. And burning hydrogen, aluminum's reactivity, even an oscillating reaction. That one's pretty cool.
And some food chemistry, too, chocolate and eggs.
Yep. And Catalysis, a Cartesian diver, finishing up with indigestion tablets. It's quite a mix.
So our mission really is to pull out the core science from all these, make chemical reactions that make sense, maybe even show some surprising bits.
Hopefully give you a few aha moments. So where should we start? Calcium carbonate.
Sounds good. That's like chalk and limestone, right?
Exactly. So the first experiment, we basically take this calcium carbonate and put it through a few changes.
Okay, like what?
First, we heat it. Really heat it up.
And what do we see?
You'll see it form calcium oxide. It's a white solid.
Okay.
Then let it cool a bit, add just a few drops of water, and then you get a reaction. It actually gets quite warm, releases heat.
Ah, exothermic.
Right. That's the calcium oxide reacting with water, forming calcium hydroxide.
Calcium hydroxide. Got it.
Then, if you dissolve some of that in more water, you get lime water. It should be clear, colorless.
Okay, clear lime water. Now what?
Now for the visual bit. You gently bubble carbon dioxide gas through this clear lime water.
I think I know this one. It goes cloudy, right? Milky.
Spot on. Almost instantly turns milky. That cloudiness is the calcium carbonate reforming. Tiny particles of it.
Wow, so it's like a cycle. You start with it, change it, then bring it back.
Precisely. And, that same basic process, just happening incredibly slowly, is what forms stalactites and stalagmites in caves.
That's amazing.
Yeah.
From this simple experiment.
Mm-hmm. And just to check that calcium hydroxide solution, the lime water, before we added CO2, if you put universal indicator in it.
It would go blue or purple. Show it's alkaline.
Exactly. Shows those hydroxide ions are present.
Yeah.
So underneath all this, it's just atoms rearranging, bonds breaking and forming.
Chemical reactions 101. Can we describe these with equations, like word equations first?
Sure. So heating calcium carbonate gives calcium oxide plus carbon dioxide.
Okay.
Then adding water to that calcium oxide gives calcium hydroxide.
I got it.
And finally, bubbling the carbon dioxide through the lime water, that's the calcium hydroxide solution, gives you back calcium carbonate plus water.
Simple enough in words. What about the chemical formulas?
Yeah, chemists use shorthand. So KCO3, that's calcium carbonate. You heat it, arrow, gives KAO plus CO2.
Calcium, carbon, oxygen atoms just rearranged.
Exactly. Then CaO plus H2O gives KOH2.
Calcium hydroxide again.
And the last step, KOH2 plus CO2 gives KCO3 plus H2O.
Back to the start. And notice how the atoms balance on both sides.
Always.
Mm-hmm.
That's fundamental. Matter is conserved. Nothing's lost or gained, just rearranged.
Okay, let's switch gears. What about those blue copper sulfate crystals? They look pretty cool.
They do. And our next experiment is about figuring out what's inside them, specifically how much water is locked into the crystal structure.
Water inside the crystal.
Yep. It's called water of crystallization. The formula is written CuSO4.XH2O. We want to find X.
How many water molecules are stuck to each copper sulfate unit?
Right.
How do we do that?
It involves careful weighing. First, weigh an empty container, a crucible.
Okay.
Then add the blue crystals, weigh it again. That gives you the mass of the hydrated salt.
Got it.
Now heat it, gently at first, then maybe a bit stronger. You watch for a change.
The blue color disappears.
Exactly. It turns into this pale, whitish powder. That's the sign the water's being driven off as steam.
Because the heat breaks the bonds holding the water in the crystal structure.
Precisely. Think of it like knocking water molecules out of a fixed arrangement. Once it's all white, you let it cool right down, then weigh it one last time.
So we have three weights. Empty crucible, crucible plus blue stuff, crucible plus white stuff.
Correct. And from those, you can calculate two key things. The mass of the water that evaporated.
Which is just the difference between the blue stuff weight and the white stuff weight.
And the mass of the white stuff left behind, that's the anhydrous copper sulfate. Anhydrous means without water.
Okay, mass of water lost, mass of anhydrous copper sulfate left. How does that give us X?
Now we need to think in terms of moles. It's like a chemist's dozen, a way to count huge numbers of molecules.
Right, using relative masses.
Exactly. We need the relative molecular mass of water, H2O, and copper sulfate, CuSO4. We use the atomic masses. H is 1, O is 16, S is 32, U is 64.
So water is 2 times 1 plus 16, 18.
Yep. And HuSO4 is 64 plus 32 plus 4 times 16. That's 64 plus 32 plus 64, 160.
Okay, water is 18, copper sulfate is a 160. Now what?
You take the mass of water you calculated, divide it by 18, that gives you moles of water.
Okay,
Then take the mass of the anhydrous copper sulfate divided by 160, moles of copper sulfate.
got it. Moles of water, moles of copper sulfate.
And finally, you find the ratio between those two numbers, moles of water divided by moles of copper sulfate. That ratio should give you a whole number, or very close to it. That number is X.
Ah, so the ratio tells you how many water molecules for every 1 copper sulfate unit.
Precisely. It's usually 5 for copper sulfate, so HuSO4.5H2O. That water really affects its properties, like the color.
Okay, that makes sense. It's a classic experiment, that one.
Definitely. Now, building on that, our third experiment looks at whether this whole process is reversible.
You mean, can we turn the white powder back into blue crystals?
Exactly. We
Yeah.
just saw heating drives off water. Can we add it back?
So we heat the blue crystals again, they turn white, but this time we try to catch the water.
Yes. We heat the blue copper sulfate in one test tube and arrange it so the steam goes into another test tube placed in, say, a beaker of cold water.
Why the cold water?
To cool the steam down, makes the water vapor condense back into liquid water so we can actually collect it.
Clever. So we heat, it turns white, we collect some water, then the key step.
Is to carefully add that collected water back onto the white anhydrous powder.
And what should we see?
You should see that vibrant blue color return almost instantly, maybe even a little bit of heat released again.
Wow. So it is reversible. Goes white with heat, blue again with water.
Perfectly demonstrates reversibility. And introduces some terms. We use hydrated for the blue crystals with water.
And anhydrous for the white powder without water.
Right. A product is just what's formed in a reaction. Condensed means gas turned to liquid, and reaction is the whole chemical change process.
So this reaction, hydrated copper sulfate plus heat, goes to anhydrous copper sulfate plus water, is reversible because it goes both ways.
Exactly. We often show that with the double arrow symbol in the equation.
Now, a thought question. Adding water back releases heat. Could you use anhydrous copper sulfate as like a hand warmer fuel or something?
Ha! Interesting idea. It is exothermic when you add water back,
Yeah.
but think about how you got the anhydrous stuff in the first place.
Ah, you had to heat the blue crystals. You put energy in.
Exactly. You put energy in to drive the water off. You get some energy back when you rehydrate it, but you won't get more energy out than you put in. Probably less, actually.
Right, thermodynamics always wins. Not very economical then?
Not at all compared to actual fuels. Good thought experiment, though.
Okay, let's move to something potentially a bit louder. Experiment 4. The oxidation of hydrogen. Finding the best bang for your buck? Sort of.
Precisely. We're looking for the most efficient mixture of hydrogen and air for combustion. We use the famous POP test.
The POP test.
Yeah. You mix hydrogen and air in different ratios in test tubes, then light the mixture with a splint. The sound tells you about the explosion.
Okay, how do we get different ratios?
We use test tubes, initially filled with different amounts of water, maybe quarter full, half full, 3/4 full. Then fill the rest with hydrogen gas collected over water.
So less water means more air trapped inside with the hydrogen.
Exactly. Then you seal the tube, take it out, and carefully bring a lit splint to the mouth.
And listen carefully to the sound.
Yes. Is it a weak whoof, a sharp pop, or a really loud, shrill squeak? Record that for each mixture.
And the loudest, sharpest pop means?
That mixture is closest to the ideal ratio for complete rapid combustion. The hydrogen is reacting efficiently with the oxygen in the air.
Okay, the reaction makes water H2O. So hydrogen H2 reacts with oxygen O2. What's the perfect chemical ratio?
The balanced equation is 2H2 plus O2 COH2O. So you need 2 molecules of hydrogen for every 1 molecule of oxygen, a 2-to-1 ratio.
But we're using air, not pure oxygen. And air is only about 1/5 oxygen, right?
Correct. Roughly 20% oxygen, 80% nitrogen.
So if we need a 2-to-1 ratio of H2 to O2, but the O2 is coming from air, what's the ideal ratio of hydrogen to air?
Okay, think it through. To get 1 part oxygen, you need 5 parts air, since air is 15 oxygen.
Right.
And for that 1 part oxygen, you need 2 parts hydrogen.
You need 2 parts hydrogen for every 5 parts of air.
Exactly. That should theoretically give you the most powerful explosion because you have the hydrogen and oxygen in the correct stoichiometric amounts.
Interesting how the nitrogen in the air just comes along for the ride, effectively.
It mostly does in this reaction, yeah. It doesn't really participate.
Okay, next up, experiment 5. aluminium reactivity, using aluminium foil and that blue copper sulfate solution again.
That's the one. We're looking at whether aluminium can displace copper from the solution. It ties into the reactivity series of metals.
Which basically says some metals are pushier than others in reactions. Aluminium is generally more reactive than copper, isn't it?
It is. It prefers to lose electrons and form ions more readily than copper does.
So the experiment, put aluminium foil in copper sulfate solution. What should we look for?
Signs of reaction? Bubbles, maybe? Color fading from the blue solution? Temperature change? And, crucially, any sign of reddish-brown copper metal forming on the foil.
That would be the displacement. Aluminium goes into solution, copper comes out.
Exactly. But there's a twist. We observe first, then we add some sodium chloride common table salt and see if anything changes.
Why add salt? What does that do?
Aluminium naturally forms a very thin, tough layer of aluminium oxide on its surface when exposed to air. It's protective.
Right. That's why aluminium doesn't corrode easily.
Exactly. But that oxide layer can also slow down or prevent reactions. The chloride ions from the salt help to break down or disrupt that protective oxide layer.
Ah, so it exposes the fresh aluminium metal underneath to the copper sulfate.
That's the idea. So we compare. Does anything happen before adding salt? And does the reaction speed up, slow down, or stay the same after adding the salt?
And how does the salt cause that change? By removing the protective layer.
Pretty much. It highlights that reactivity isn't just about the metal itself, but also its surface condition and environment.
Makes sense. Okay, moving from reactivity to, well, something visually quite different. An oscillating reaction. Number 6.
Oh, yeah, this one's a crowd pleaser. You mix a few solutions together, and the whole thing just cycles back and forth between typically red and blue. It's quite mesmerizing.
How does that even work?
It involves a complex set of interconnected reactions, usually uses specific chemicals, often labeled solution A, B, C, plus an indicator called ferroin, and maybe a drop of something called photoflow.
The instructions mention it might go brown initially, then that fades before the oscillations start.
Yeah, that's like an induction period. The chemicals are reacting, concentrations of intermediates are building up, getting ready for the main cyclical process to take over.
And ferroin, that's the indicator. What's its role?
Ferroin contains iron, and its color depends on whether the iron is in an oxidized state or a reduced state. It's a redox indicator.
Redox. Reduction in oxidation. Electron transfer.
Exactly. As the concentrations of other chemicals in the soup rise and fall cyclically, they cause the iron in the ferroin to switch back and forth between its oxidized and reduced forms, changing the color from red to blue and back again.
So the color change we see is directly linked to these electron transfers happening.
Beautifully linked, yes. It's a macroscopic view of microscopic processes.
And photoflow. It says it's a surfactant. Like soap.
Sort of. Surfactants reduce surface tension. In this case, it helps the solutions mix really well and evenly in the Petri dish. Makes the color changes smoother and more uniform across the whole thing.
Got it. So, complex chemistry, but a really striking visual effect.
Definitely one to see if you ever get the chance.
Okay, let's bring it back to the kitchen. Experiment 7. Chocolate and egg. What happens when you heat them?
This is great for showing the difference between physical and chemical changes using everyday stuff. Simple setup. Put some egg white in one tube, chocolate in another, stand them in boiling water.
And just watch what happens.
Watch what happens as they heat up. And then importantly, what happens when they cool back down. Make notes, maybe in a table.
What should we look for? Texture, color, state?
All of that. Egg white goes from clear liquid to white solid, right?
Yeah, it could.
Chocolate goes from solid to melted liquid.
Okay, then we let them cool. Does the chocolate go back to being solid?
It should, yes. Maybe not the exact same shape, but chemically it's still chocolate.
But the egg white, it stays cooked, stays solid and white.
It does. You can't uncook an egg just by cooling it.
So this shows the difference. Which change is physical, meaning reversible?
The melting and re-solidifying of the chocolate, it changed state, solid to liquid back to solid, but it's still chocolate. That's physical.
And the egg cooking, that must be chemical, irreversible, new substance formed.
Exactly. The heat denatures the proteins, changes their structure permanently, forms new bonds. That's a chemical change.
Can you give another quick example of each? Physical and chemical.
Sure. Physical, ice melting to water, still H2O. Chemical, burning wood. You get ash, smoke, CO2, completely new stuff.
Simple but really fundamental distinction. Okay, experiment 8. Catalysis. speeding things up.
Right. We're looking at a reaction between iron 3 nitrate and sodium thiosulfate. It makes the solution go cloudy over time.
And we measure how fast it goes cloudy.
We use a visual trick. Put the beaker over a piece of paper with a cross drawn on it. Time how long it takes for the cloudiness to completely hide the cross.
Okay, that's our baseline speed.
Then we repeat the experiment, but add a tiny bit of different metal salt solutions like nickel sulfate, copper sulfate, iron 2 sulfate, cobalt chloride, one for each run, and a control run with no added salt.
And if one of those makes the cross disappear faster,
then that metal compound is acting as a catalyst for this reaction. It's providing an easier pathway, lowering the activation energy.
So we record the times for each one and compare. Which one is the best catalyst?
Whichever one gives the shortest time. The catalyst itself isn't used up, remember? It just helps the reaction happen faster.
Why use only very dilute solutions of these metal compounds?
Good question. 2 reasons, really. 1, catalysts often work effectively even in tiny amounts. 2, using dilute solutions ensures we're seeing the catalytic effect, not some other reaction involving the metal salt itself as a major reactant. Keeps it focused.
Makes sense. And if we wanted to slow down this reaction, what could we do?
The simplest way is usually to lower the temperature, cool it down.
Less energy in the molecules, fewer effective collisions.
Exactly. Lower kinetic energy means fewer molecules have enough energy to get over that activation barrier, even with a catalyst present. So the rate drops.
Okay, nearly there. Experiment 9, the Cartesian diver. This sounds like physics.
It is, named after René Descartes. It's a brilliant demo of how pressure affects gases and liquids.
How do you make one?
Usually a small pipette or dropper with a little water inside, maybe weighted with a hex nut or clay, so it just barely floats in a sealed plastic bottle full of water.
Just floats? Okay. And then the magic happens.
You squeeze the sides of the plastic bottle.
And the diver sinks.
It sinks down. Then you let go of the bottle.
And it floats back up. How?
Okay, when you squeeze the bottle, you increase the pressure inside on the water.
Right.
Water doesn't compress much, but that pressure gets transmitted everywhere, including onto the little air bubble trapped inside the diver.
And air does compress.
It does. So the increased pressure squeezes that air bubble, making it smaller.
But the diver's weight hasn't changed.
Correct. Same mass, but now a smaller volume because the air bubble shrunk. Smaller volume means higher overall density.
Higher density than the water. So it sinks.
Bingo. Then when you release the pressure,
That pressure drops. The air bubble expands back to its original size,
lowering the diver's overall density again?
making it less dense than water, so it floats back up.
You got it. Simple materials, profound physics, shows Boyle's law in action, really pressure and volume of a gas, and buoyancy.
That's really neat. Okay, last one. Experiment 10. Indigestion tablets. Back to practical chemistry.
Yep. Finding out how much acid one of these tablets can actually neutralize. Quantifying its effectiveness.
How do we do it? Crush a tablet first.
Crush it up, dissolve it in some water, then add an indicator methyl orange usually.
Why methyl orange?
It's yellow in alkaline or neutral solutions, but turns red in acid. The tablet contains alkaline stuff, so it'll start yellow.
Okay, yellow solution. Then we add acid.
Carefully, from a burette. Add acid of a known concentration, drop by drop, swirling until the solution just turns permanently red.
That color change means?
It means you've added just enough acid to neutralize all the alkaline stuff in the tablet. The solution has just become acidic. That's the endpoint.
And we need to know exactly how much acid we added.
Yes, record the volume of acid used from the burette, and you already know its concentration. That tells you how much acid the tablet neutralized.
Okay, so now the practical bit. If we had different brands of tablets and their prices, how could we use this experiment to find the best value?
You'd run this neutralization experiment for one tablet of each brand. Find out how much acid each brand's tablet neutralizes.
Okay.
Then you look at the cost per tablet for each brand. You can calculate a neutralizing power per penny or per dollar.
So divide the amount of acid neutralized by the cost.
Essentially, yes. The brand that neutralizes the most acid for the least money is the best value, scientifically speaking. Moves beyond just the advertising.
A very practical application of titration. Okay, so that's all 10 experiments. Wow. Quite a journey.
It really covers a lot of ground, doesn't it? From basic reactions like the calcium carbonate cycle
To things like finding chemical formulas, reversible reactions, combustion ratios.
reactivity, catalysis, those cool oscillations, physical versus chemical changes in food.
Even pressure effects with the diver and practical neutralization.
It really shows how even experiments that seem quite simple on the surface can demonstrate some really deep scientific ideas.
Absolutely. Hopefully, looking at them this way gives a clearer picture of the chemistry and physics happening all around us.
Yeah, these aren't just lab tricks. These principles are everywhere.
So a final thought then. Maybe consider how these controlled examples, equilibrium, reactivity, catalysts, pressure, conservation of matter, play out in bigger, messier systems.
Yeah.
Like, in nature or industry or even inside us.
That's a great takeaway. Once you start looking, you see these chemical and physical principles working everywhere, often in ways you didn't expect.
Definitely something to think about. Well, thanks for joining us on this deep dive.